hope so. Yeah, I think I am. I think that's where it would have been. Okay, sorry, wasn't paying attention. I was talking. Let's get set up from current slide. All right, I think we are recording and we're got a slide up, so let me go over a couple of more announcements. These are nothing too major, but if you notice, you may have, that maybe grades weren't posted last week, and yeah, I don't know if you noticed it. Attendance wasn't posted last week. Usually I try to do that. If I can't get it done during the week, I get it done on Fridays. Friday I was at a meeting all day long. We left Birmingham campus. Well, I was over there before 6 o'clock. We left shortly after 6, around 6:14 or so. Drove to Opelika. We were in meetings all day. Drove back. It was close to 6 o'clock when we got back. And over the weekend, didn't have much opportunity to get things updated. I did get some grading done. In fact, everything that y'all turned in has been graded. I'm on the Tuesday, Thursday classes. I still don't have all that graded, but my Monday, Wednesday classes are up to date. But I haven't been able to get on Blackboard to put them in. Hopefully, knock on wood, today I have office hours from 3:15 to 5:15. And if nothing else pops up, I hope to get those caught up then. Okay, hopefully. Okay, and number 2, coming up this week, we have, I have my annual physical Friday morning at 8. So again, I won't have a full Friday on campus, but unlike the last 2 Fridays, it won't be a total washout. I will be, hopefully the physical won't take more than an hour, so hopefully I'll be back on the Birmingham campus by 9:45, 10 o'clock or something like that. Now, last time I had a physical, can't remember what it was. I think I happened to get my flu shot at the same time, and the nurse who gave me the flu shot stuck herself. So therefore, it was her fault, but then I had to go through blood work so she could make sure she wasn't exposed to anything through me. So I thought I'd like to know if, well, she did it after she gave me the shot, so there wasn't any chance that I was exposed to anything through her. So I had to go and sit so you never can tell. Something dumb like that. I've already had my flu shot, so hopefully nothing like that will come up. Now, they could request, and I hope I can talk my doctor out of it, me to go through and have blood work done, and that doctor only does it after the examination. It seems like to me it'd make a lot more sense for him to do the blood work beforehand, so then he could look at the numbers and say, oh, well, we need to deal with this or that, or everything looks fine. But this one does it afterwards, after he examines me, then he decides what kind of blood work. And I guess it saves them money that I don't think we need to do this or that or that. So anyway, it could be he's going to want me to have blood work, but since I go in to the hematologist, I'll be visiting him within the next month. I'm going to try to talk him into just requesting the blood work to be done with that draw rather than having to do it this Friday. He usually is really reasonable about that. So hopefully we can talk it into that as long as the nurse doesn't, well, whatever. Okay, anyway, I will be away from campus some. Now, at UAB, I can sometimes get some stuff done. Their public server sometimes gets really crowded, but usually 8 o'clock in the morning, I can get on and get some things done while I'm in the waiting room and stuff. So I'll try to get a lot caught up then. Yeah. Yeah.
It sent an email to somebody take a graduation exam.
Okay, yeah, okay. Let me talk about that. It's called the CAP exam. And let me see if I can remember what that stands for. Collegiate Assessment of Aptitude Program or something. It's CAAP. And what it does, it measures your proficiency in reading, writing, and mathematics. Okay, that's it. You know, there's English part, a reading part, and a math part. and it's just a standardized test, and it gives us a measure, an idea of how we have prepared you to go on to the next level. Gives you an idea places that you might need to work. I don't think any four-year schools look at it per se. They might, they could, but I think they have to request to look at it if they know that we gave it. But it mostly is a way that we measure our I don't think so. I don't know for sure. It seems like I'm guessing around 2 hours, but I'm not sure it's that long. Because there's 3 parts. Something sticks in my mind like 40 minutes each part. So that would be 120 minutes, and that would be close to 3 hours. But that may be just something floating around in the ether space here that I don't know. But I think that's what it is. But yeah, go take it. It's not going to hurt you, but do your very best you can. Make us look good. Make us proud, you know. And then if it is something, you come out with a really good score, you can use it and brag about it. Well, I scored in the upper 75 percentile or 80 percentile or something like that on this thing. And someone look at it, hey, that's pretty good, you know. So I encourage students to go into it with a really positive attitude, do the best they can. It's not going to hurt you any, but it has potential to be a boon, a benefit to you. Yeah, glad you asked that. I always forget about that. This is what gets me too. As far as I know, they don't do it for summer and fall graduates. They only do it for spring. And yeah, but I may be wrong on that, but that's the only time I hear about them doing it. And I like to use that as a measure of our student learning outcomes. You know, our graduates scored this level on the CAP exam. The trouble is getting that information from whoever gets the information is like pulling teeth, and sometimes they claim it's not back until after we have to do our student learning, assessments. But I like to use the data because I do look at it and see how our graduates are doing in mathematics specifically, because that's the one that pertains to me. But yeah, so do your best. RB will find you. Okay, yes. All right, any other questions? Good questions so far. All right, let's pick up where we left off last time, which was on page 66, Chapter 2, Section 2.3. Chapter 2 is matrices, Chapter 2.3 is inverse of a matrix, and we were on example 5. And what they gave was a couple of, let me get my pen. Well, where is my pen? Come here, pen. There we go. All right. Yeah, okay. Here was matrix A. 3, -1, -2, 2. Now, I know last week was a long time ago, but we talked about how to get the inverse of a matrix. So far, we have 2 ways. 2 by 2, pretty, okay. For 2 by 2 matrices, we have 2 ways. Actually, we did a 3rd way. The 3rd way is a really long, complex way. 2 by 2 won't be that bad. Much easier to do. Adjoin that with a identity matrix and go. But for 2 by 2 and 2 by 2 only, there is even an easier way. Does anyone remember what that easier way is? I knew it was too long ago. I mean, at least 4 days. 5 days, something like that. Wow. Okay. Okay, that's how we start. What that's called is the determinant. Determine the determinant of matrix A. And what is that? Say again? Okay, how did you get that?
Oh, I was just doing the numbers. I thought you said numbers is in the
the determinant is the main diagonal, product of the main diagonal, 6, minus the product of the other diagonal. Okay? And that would be minus a 2. 6 minus 2 is 4. Very good. Okay, that's where our problem came. All right. Okay. Our determinant is 4. What do we do with it? Well, no. Time out. What do we want it to be? Well, it's going to be one of these things or another. Okay? Either it's going to be 0 or not 0. That's what we look for. And this is obviously not 0. Therefore, that matrix does have an inverse. If and only if that determinant was 0, would that matrix not have an inverse. And since it does have an inverse, it does have a matrix, we can go to the next step. And what is that next step? And let me, I didn't leave enough room. Okay, what did you say? 1 over 4 times no, we're looking for the inverse. Say that again. I can't hear you a little. Okay, that's one part of it, but not everything. First thing, say again. Okay. Now, what do you flip? Flipping, I think, is okay, especially if you're working at Waffle House, you know, but no, never mind. Okay. What do you flip? The main diagonal. Exchange those two, 2, 3, and then you negate the off diagonal, and that would be 1, 2. Okay? And then, if you wanted to, you could multiply through by your 1/4, and this matrix would then be 1/2, 1/4, 1/2, 3/4. Okay. Now, how would you try to convince me that was indeed true? That this was the inverse? Multiplied. Okay? Now, frankly, I love fractions, but Nigel, he really loves them, okay? If I remember correctly, okay? And what we're going to do, or what I suggest doing, is not multiplying those two, but multiply these two, and then we'll take 1/4 of it, of that answer. Once we mark markers here. Okay. One more and we'll have perfect attendance. Okay. So let's multiply these two matrices. Okay. What would that give you? Can you multiply them? Okay. And what size would you get? A 2 by 2. Okay. Which one you want to do first? Which entry? Okay, 1, 1 entry. Okay, row 1 times column 1. What does that give you? Okay, we've just determined what we think is the inverse of this matrix, that matrix. Okay, now we're checking it, and how we're going to check it is not multiplying this one by that one, multiply this by this, and then multiply by 1/4. Okay, and what do you get? 6 minus 2 is 4. Okay, we'll buy that. Next, you want to do the 1, 2. Okay, that would be 3 minus 3. Sure enough is 0. 2, 1. That would be 6 minus 6. That's 0. Yeah. Okay, and then 2, 2. And 6 minus, 6 minus losing my frame of reference here. 2 minus 6. Yeah, that's it. Minus a minus, wait. Oh, yeah, I got it. Negative 2 plus 6. Brain's not working well. My eye's not working. Then we can take 1/4 of that, and what do we get? The identity matrix, which confirms that this is indeed the inverse. Now, if you really wanted to confirm it, you could then multiply the other way. I'll take the word for it, okay? That indeed is it. Notice how easy that was. First thing we do, take the determinant of the matrix in question. Why do we take that? There's 2 reasons. If it has a inverse, and what would tell you that? If it's 0, it doesn't. If it's not 0, it does. Absolutely. But it also does one other thing for us. If it's not 0, then that's what is the coefficient of the matrix we're going to come up with next. And what is that matrix? This only works for 2 by 2s. Reverse the order of the main diagonal, negate the off diagonals. Exactly. Doesn't work for anything but a 2 by 2. Okay. Let's try B. Here's matrix B. 3, negative 1. Negative 6, 2. Can any of you look at that and without doing anything else tell me whether to proceed? If not, let's proceed. What would you do first? Determine the determinant. And that would be what? 6 minus what? Okay, 6 minus 6, which is? 0. Okay? Therefore, don't go any further. Not an invertible matrix. It's a singular matrix. Does not have an inverse. If that determinant comes up being 0, not. Now, I was going to wondered if you just, when you looked at this, you could tell. 2 by 2s, you can. Bigger ones, you can. But, and sometimes it's hard to tell, but when I looked at this and saw that this was exactly a multiple of that, in other words, multiply this one by negative 2 and you get that row, guess what? That represents, if you had them, if this was a system of equations, a dependent system. Dependent systems will have infinitely many solutions, therefore they're not going to have it's not a invertible matrix. Okay? You probably haven't gotten enough to know that yet, but if you thought about row reducing this one, which is what we would do the other method, multiply the top row by, I'm not going to divide by 3 yet. I'm going to do that later. Multiply the top row by negative 2, add it to the second row, by 2 and add it to the second row, this becomes 0, 0. Guarantee that's not ever going to be a 0, 1 then. Okay, remember that's when you did the other method, you adjoined this with a identity matrix, do your row reduction, you want an identity matrix here, and what's left over there is your inverse, right? If you think about this, multiply this by 2, add it to that one, you'll never get a 0, 1. You'll get a 0, 0 every time. So, if one of these rows is a multiple of the other, for 2 by 2s, you can immediately say, not invertible. Okay? Make sense? All right. Just as easy to do your determinant. But just looking at it, I could tell the other. I have to actually think a little bit. Well, I thought both times. All right, let's move on to properties of inverses. Here are some important properties of inverse matrices. Okay, the given is A is an invertible matrix. Tell me one thing that communicates to you right now. There's several things that should communicate, but you tell me one thing. It's what? If you see it's an invertible matrix, if you're given it's an invertible matrix, what does that tell you? It's a square matrix. It's got to be. You cannot have a rectangular matrix. It's not a square and have it invertible. It can't happen ever. Okay. So one thing immediately pops into my mind. It is a square matrix. Okay. What's one other thing that should pop into your mind? Oh, wait, no. Yeah. Well, it's true, but it's only useful if it's a 2 by 2. But if it would be a 2 by 2 matrix, it also means, but actually it's true for any matrix. If its determinant is 0, not invertible. So therefore, the determinant of this matrix is not 0. So if it says it's invertible matrix, you know automatically the determinant is not 0. Now that may not be useful to you for bigger matrices, square matrices, but you know it right now. Okay, you know it's square and you know its determinant is not 0. Okay, the second part they give you is that K is a positive integer. I can't write a plus most of the time without writing a minus under it, so I've gotten so used to doing that. Plus or minus, is a positive integer. Okay? K is a positive integer. It's a constant, but not just any old constant. It's an integer, but not just any old integer. It's a positive integer. Okay? Now, that's the K. The C is a non-zero, let's see, how do I do that? Is not zero scalar. Now, what does that mean? C can be any real number in the world. Positive, negative, fractions, decimal, rational, irrational. It just can't be 0. That's the only restriction on it. K can't be positive or negative. It's only positive. Can't be fraction or decimal. Only integer. Positive integer. Can't be rational or irrational. It's got to be a positive integer. But C just can't be 0. Okay. And by the way, K can't be 0 either. 0 is not a positive or negative integer. It's an integer, but not a positive. So, if all these are true, then this implies that a inverse exists, obviously, because it's an invertible matrix. A to the K can be done, because you can multiply any square matrix by itself as many times as you want, as long as K is a positive integer. Okay. CA, of course, exists too. You can multiply any invertible matrix by a non-zero scalar, and A transpose. Now, we've just talked about that recently, but this is what's given, that these are all invertible. Every one of those is invertible. And the following are true. Not all are they invertible, but these are true too. You tell me what you think the inverse of the inverse of A would be. If A inverse is invertible, what would its inverse be? It would have to be A. Very good. Okay? Number 2. Okay? If you did A to the K, which you know is an invertible matrix, that's what it just told you, what is its inverse? Say again? Can't hear you. Okay? It would be the inverse of A, that's the first part, but that would then be raised to the Kth power. Okay? Now, I don't know if that's intuitively obvious to you. It looks like it makes sense, but remember, this is raising this matrix to a power, basically. It's A times A times A times A times A. This is not raising A to a power. That's an inverse. So, or this is, that's not raising it to a power. But, indeed, what it appears to be doing, because if these were both powers, if it's A to the K to the L, then that would be the same as A to the L to the K, A to the LK. That would be true. But, even though this does not represent the same thing as this, you can interchange. So that's sort of maybe not intuitively obvious, maybe it's something you would hope would be true. This is saying, indeed, it is true. That's pretty obvious. It's got to be true. Okay? This is saying the other is true as well. How about this one? C to the A. We've just said that's invertible. So what would be the inverse of that matrix? All right. It's the inverse of C, and that's the multiplicative inverse of C. Remember, a matrix, that's not a multiplicative. Well, it sort of acts like that, but you can't just do that to a matrix. But 1 over C times what? A inverse. You got it. Which, hopefully within your heart of hearts, you would think, yeah, I want that to be true, okay? You may not have thought what to do with that C, but that's what you do with it. Invert the C multiplicatively, and then do the inverse of A. And then we also were told that A transpose is invertible. So what does that mean? If you took A transpose and invert that, what would you hope that meant? Basically, looking at the same type thing we did here, you would hope that would mean that would give you A inverse transposed, and indeed it does. Even though this is not a power, that's an operation. That's exchanging rows and columns, right? That's what this is. It's not the same as A to K. A to K is actually multiplying A times itself K times. This is exchanging the rows and columns. And if you take that invertible matrix and invert it, what do you get? Well, this is an operation. That's an inverse operation. This is a transpose operation. They have really nothing to do with each other, but can you exchange them? This theorem says, yes, you can. That's what you get. So hopefully nothing here is surprisingly new. Hopefully you would say, oh yeah, that's what it should be. Okay? Even though they are completely different operations. And you notice what's not consistent about what I did on the board. I circled my 2 rather than doing parentheses, okay? Not parallel structure. Never mind. It's just dumb. Okay. Any questions on that? Now they say the key to the proofs of properties 1, 3, and 4 is the fact that the inverse of a matrix is unique. Okay? That is, BC is equal to CB, and that's equal to 1. So you're going to use that when you're proving these. Okay? Property 3, it does that too. And perfect attendance, ding, 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 ding. All right. Jonathan's here. All right. We're in Chapter 2, Section 2.3, on page 67. We just finished talking about the properties of inverse matrices. We looked at 3 of them. And now they're doing basically the second one, I take it. No, it says properties 2 and 4 are left for you to prove. So they're moving on to something else. So we just finished those. If you can't catch it all here, it will be on YouTube videos a little later. Generally, I can't get these to the YouTube videos until the end of the day, which is around 3:15 or so. Something else I do at 3:15. There's lots of things I do at 3:15. So as soon as my 4th class is over today, I start moving them to the playlist. So you won't be able to access it before maybe 3:30 or so. Well, yeah, certainly by 3:30 I'll have to have it done because another class comes in here at 3:30. So I'll try to get it done shortly after 3:15. They should be. Yeah. Because I got all but Thursday evening's class moved. So yeah, I got all Mondays and Wednesdays moved. The first 3 classes are usually done through by the time I get the end of the 4th class. Fourth class usually isn't, so I have to wait till the next day to upload to get it into the right playlist. But usually by 3:15, unless I've got something else going on that I can't do it, I'll get them done by 3:15 every day. Mondays and Wednesdays, okay. Tuesdays and Thursdays, I've got a little bit of time between 10:45 and 11. Yeah. No, what? The CAAP. Okay, that's what we were talking about earlier. Y'all must have just gotten this email, right? Okay. I take it that at least 2 or 3 of you graduating this term? You are? Okay. So listen up, it pertains to you too. You're not graduating this term, are you? It's your first term here, right? Or second, okay. The CAAP is Collegiate Aptitude and Achievement Proficiency, or something like that. That's what it stands for. What it is a test that measures 3 areas: English, reading, and math. Okay? And what it does is lets us know what kind of job we did in the 2 or so years that we've had you. But what it also does is let you know where you stand in those things. So if you're areas that you need to improve, you might know that consider doing that before you go to a 4-year school. And I think most of the time 4-year schools don't particularly have access to it unless you give them access. But if you come up with a really good score and you want to use that, say, in a scholarship application or something else, or even admission application, and you want to brag on it, use it, So what it is a standardized test, I think done by the college board, same folks that do either SAT or ACT. I think that SAT, I'm not sure. One of those two, same group. And all graduates in spring term are required to take it. And please take it seriously. Do as well as you can in it. It can't hurt you, but it can potentially help you. So please do your very best. And we would love to have the fairest reading of what you've achieved while you're here. Okay? So go, they set aside times for you to do it. They give you multiple times you get to choose. Just as the term rolls around, have they given the days yet? Okay. Are they late April or so? Oh, March. March or April 17th? Huh? April. Okay, yeah, that's what I thought. Usually they're given toward the end of the term, but they give you multiple times that you can take them. They have suggested times to try to get so everybody doesn't take it at the same time. I don't even know why they bother, because not everybody taking the same course is going to have the same schedule anyway, so they can't take them all at the same time. So take them whenever you can.
So you can't take more than one time.
You mean in that week?
No, I'm just saying before you graduate. You take it more than one time. You say one time.
No, they just give you alternate times you can take it.
Oh, okay.
Yeah, no, you take it once and then you don't have to take it anymore. No reason to. Okay? Now, I bet you they have some website out there you can go and look at sample questions and be prepared when you go in for what to expect, rather than going in completely blank. Oh, they're asking that? Oh, I wish I'd have looked at this, So I bet you there are some sample questions out there somewhere. I don't know where to send you. Y'all are better at that than I am, You can search and find. So they may not have it, but I would think most things do. So do your very best. For our sake, but also for your sake. All right. Now, was there more questions? Okay. For non-singular matrices, what's another word for a non-singular matrix? Another word for non-singular matrix. Say again? Invertible. If it's non-singular, it is invertible. If it's singular, it's non-invertible. Those are the two sort of opposite things. Why they have two names for it is just for two different applications. So for non-singular matrices, as soon as you read that, you think invertible matrix. When you think invertible matrix, you think square matrix, okay? All right. And that means they have an inverse, right? And they also means the determinant of that matrix is not 0. But that's not really super important here. For non-singular matrices, the exponential notation used for repeated multiplication of square matrices, notice there they put square in italics there, can be extended to include exponents that are negative integers. I can't talk, okay? This may be by defining, okay? Now this actually follows on to number 2 here. You could call either of these a to the minus k, okay? Most of the time we don't, but that's what it means, okay? That means a to the minus k would then mean a to the minus 1 times a to the minus 1 times a to the minus 1 times a to the minus 1 if these are a total of k factors. That's exactly what that means, okay? So that would be a to the minus 1 to the k. And then from this, that tells you also that's a to the k to the minus 1, because from up here, this says that's the same as that. All right. Using that convention, you can show that the properties of, I need more room, so I'm going to have to clean this. I know I'll need something that's on there later, but okay. A to the j times a to the k, a to the j to the k, I'm sorry. That's what I'm trying to prove. A to the j times a to the k is equal to a to the j plus k. We knew that. We talked about that before. But when we talked about it before, we had j and k only being positive integers. Now we can extend that and let j and or k be negative integers. Okay? So this just expands and extends what we know. Okay? It also, a to the j raised to the kth power, which we did before for positive integers. What would that be for any integers? A to the j times k. When you raise a power to a power coming through the right, then you multiply the powers, just like you do for numbers. And now that's not true just for positive integers, which it was before, any integers now. Okay. Now, I have one very little issue with this, but maybe it's already taken care of. I just can't remember. Did we define what a to the 0th power was? We did? Okay. It is the identity matrix, but I couldn't remember if we had talked about that before. Just like a number a, any variable thing to the 0th power was 1, if j or k in either case here was 0, then that would be the identity matrix. As long as we had done that, I couldn't remember if we had or not. I knew it, but I couldn't remember if we had done it before. All right, so let's do this little discovery here. These are always so much fun, aren't they? You don't have to answer that question. Here's A. Another matrix A. 1, 2, 1, 3. And here's matrix B. 2, negative 1. 1, negative 1. I think we've seen them before, but maybe in different contexts. The first thing it says is to calculate AB inverse. So what would be the first thing we would need to calculate? Second? Okay. Oh, wait. Let me put my parentheses correctly here. Just to be less ambiguous. We try to be as ambiguous as possible. Okay. It's AB to the negative 1. Okay. Now, according to the way they've written it, what would be the first thing we would do? Multiply the two together. So let's first figure out what AB is. Can you multiply those two? Answer, sure. And what size will it be? 2 by 2. We knew that. And what would be the first entry? Say again? Really? I get it. Okay. 4. Okay. Good. Okay. I thought my mind is really not with me today. Okay. What would be the 1, 2 entry? Anyone know it? Did I hear a negative 3? Okay. Yes. Okay. My hearing's bad, so I have to check. Okay. 2, 1. 5, 2, 2, 'Did I hear a suggestion yet? Negative 4. Got it. Okay. That's AB. We still need to do the inverse of that. Anyone remember a nice, easy way to do that? First thing we would do would be to say again? Find the determinant. And what would that be? Negative 16. What's that? Okay. The determinant of a matrix, yeah, we did this before you came in, but we did it last week as well. The determinant of a matrix is the product of the main diagonal minus the product. And this, okay. You only do this for 2 by 2 matrices. You can take the determinant of a bigger matrix, but it's a much more involved process. So we usually don't, okay? But for a 2 by 2, it's so easy to do, we do it. The determinant of this matrix is the product of the main diagonal, in this case a negative 16, minus the product of the other diagonal, anti-diagonal. And that would be minus 15, but it's the minus of minus 15, which would be plus 15, so this would be a negative 1. So the determinant is negative 1. Okay? Now, so what? Okay, let's go over this too. That tells you one thing right off the top. If that determinant is 0, this thing doesn't have an inverse. Period. But if this thing's anything other than 0, it does have an inverse. Okay? So the first thing it tells you is whether it has an inverse or not. If it's a 0, it doesn't. If it's not a 0, it does. This is not a 0, it's a minus 1. So the second thing that tells us, when trying to find what that inverse is, we multiply this matrix by 1 over the determinant, which would be 1 over a minus 1, which of course is minus 1. Times, now this works only for 2 by 2s. Don't try it for anything else, it won't work. But it does work for a 2 by 2. And what do we put next? Okay, the next thing you do is exchange your main diagonal elements. Put the minus 4 up here and the plus 4 down there. And then what's the second thing we do? Say again? Okay. It's 1 over the determinant. That's what we always do. Once we found the inverse, and it's not 0, you put 1 over that determinant. That's what that was. Okay? Now we fiddle with the entries. Okay? What do you say it would be? Positive 3, negative 5. You exchange the main diagonal elements and you negate the off diagonal elements. Okay? Only for 2 by 2s. Don't try it for anything else. Only for 2 by 2s. Now we multiply through by that, and the coefficient here is a -1. So what does that give you? 4, negative 3, 5, negative 4. Whoops! What do you notice here? It's the same matrix as what we started with. Okay? The same product that we started with. Okay? Let's do this one now. A inverse, B inverse. Okay? First, let's do A inverse. What would A inverse be, by the way? I think I'm going to go back just because it's in my way. This is where we calculated the determinant of the other, but since I didn't have anything with it, I'm going to. Okay. Say again? What is 1? Oh, okay. He's doing the determinant of A. A great thing to do. 3 minus 2 is 1. So the inverse, the determinant of A is 1. So we could put a 1 over 1 in front, but why? Let's just do it. What's the next thing you do? Switch the main. That will give you 3 and a 1. Negate the off diagonal, negative 2, negative 1. Okay, there I've got my inverse of A. Now let's do the inverse of B. Okay, what would you do first? Determinant of B, and that would be negative 1. So the determinant of B, that's the symbol for determinant, negative 1. So this will be times 1 over -1, which is going to be a -1, times, and then how do you fiddle with this? Say again? Okay, you're negating at the same time? Or not? You are, okay. I'll take that out, and what do you get? Negative 2, okay. Negative 1, Okay, because you're exchanging them, okay, he's doing it all at once, remember? You exchange them, that makes that the +1, that's the -1, then we multiply that by -1, that becomes a -1, that becomes a +1, right? Okay, so there we have that one. Now, if that was too many steps at once, blame Nigel, okay? Don't blame me, okay? It's his fault, okay? Now let's multiply those two together. Can we multiply those two together? Good deal, thank you. Can we multiply those two together? Answer that question. Yes. And what size will it be? 2 by 2. So let's do the 1, 1 entry, and what do we get? 1. Next. Second. Okay. Multiple choice for me? Okay. What would it be?
I don't know. Can you go back to the determinant for B?
Say that again. Okay, we go back to the determinant for B. Okay, that's going to be minus 2 plus 1.
This time gonna be negative 2.
Okay.
Or we're not multiplying, are we? Like
Okay.
2
You
times-
multiply is the product of these minus the product of those.
Okay, fine.
Yeah, that's determinant. Yeah, we mess around with rows and columns, and sometimes it's pluses and sometimes it's minus. You just have to keep straight what it is. In multiplying, you're adding everything.
Okay.
Okay. With determinants, you're taking a difference. Okay. So let's do 1, 2. Did we ever decide what that was? One. Okay, good. How about 2, 1? Second. 0, is that what you said? I can't hear. Okay. Next. Yeah, negative 1. Okay. So there we got A inverse times B inverse. All right. I'm not absolutely certain why they had us do that, but they did. All right, and the third thing we want to calculate is B inverse times A inverse. So basically, we're going to reverse these two. So we're going to do, I just don't have enough room. So B inverse times A inverse would then be 1 minus 1, 1 negative 2, times 3 negative 2, negative 1, 1. Okay, I know that's awfully small and crowded. Let's do that. Can you do it? 2 by 2. What will they be? 4. Negative 3. 5. Negative 4. And we know these are going to be the same. We've already done that before. The AB inverse is the same as B inverse A inverse. Okay? So why did they have us do that before? Make a conjecture about the inverse of a product of two non-singular matrices. Make a conjecture about the inverse of the product of two non-singular matrices. Well, it's an invertible matrix. Maybe there's something more they want. Select two other non-singular matrices and see whether your conjecture holds. Maybe the conjecture is involved that it's the product of the inverse of the second times the inverse of the first. But we had already done that, so I don't know why they had us do it before, but just to reinforce it in our brain, I guess. Okay.
Can I ask you one more question?
Sure.
Okay,
You just did. No, I'm just kidding. Okay.
well, you know how you swap the main back? So like,
Okay, when you're doing the inverse.
Uh-huh.
Yeah, of a 2 by 2 only. Okay, yeah.
So like you have, for B, for example, you got like 2, and then you have
Right here?
You have 2, and then you have negative 1. So how did that turn into like a negative 2?
Okay. Yeah, okay. I've skipped a step. Nigel made me. Remember, it's his fault, not mine. Okay? What you do is 1 over the determinant. We determined the determinant was 1, so this is 1 over a negative 1 times, and then you exchange the 2, minus 1, 2, and negate the other 2, 1 minus 1. Okay. This is a minus 1, right?
Okay, so it basically changes
Yeah.
the sign of it.
So that changes that to plus, plus, minus, plus, plus, minus, minus. But Nigel insisted on doing it all at once. I think the reason was to confuse you. I could read his mind. He said, let's see if we can confuse Jonathan. He wasn't here earlier. Okay. See,
That makes sense.
yeah, we did too many steps at once, sort of. Okay, but we're trying to be as lazy as possible, is what you said, wasn't it? Okay, let's move on to example 6. Can I move now, or do you want this up a little longer?
No, I get it.
Okay. All right. Example 6. Compute a to the minus 2 different ways and show that the results are equal. So we're looking for a to the minus 2 when a is 1, 1, 2, 4. Okay. Tell me what 2 ways you're going to do first. Symbolically, what would you do? Okay, no, symbolically, what would you do? A to the minus 2. Say again? A squared to the minus 1, take the inverse of that, or the other would be take the inverse of A. Why am I putting it in brackets? That's a little confusing, so let me put them in parentheses. I'm so used to doing brackets for matrices. Squared. Either one of those 2 ways. So which way you want to do first?
So why did you do that?
Second?
So why did you do that?
Why did I do it? They told me to find that 2 different ways, and I just said, those are the 2 ways I'm going to do it. Can you think of another way you'd like to do it? Okay, all right, so that's what we're going to try. And besides, it's his fault. Emmanuel told me I had to write that down. So if it turns out wrong, it's his fault. Okay, so what are we going to do? You want to do the first one first? So how do you find a squared? A times a. I think I can do that. Okay, and can you even multiply those 2? And what size would it be? 2 by 2, so sock it to it. 3. 5. 10. Second. 18, okay. My hearing's so bad. All right. Now what's the next thing we got to do? Take the inverse of that, and what would be your first step to do that? First find the determinant of that, and what would that be? Ew, big numbers, aren't they? $74. Ooh, okay. Is that right? Something doesn't seem right there. Huh? Wait. Let me, I don't buy that. Uh-huh. Wait, what's 3 times 18? Is what? 54. Okay, I thought you said 74. Ah, got it. Okay. Minus 50. My hearing's bad, but I knew that wasn't right. Okay, so that's going to be 4. So the determinant is 4. So what do we do with that? 1 over 4 times 18, 3, not negative, okay, yeah, negative 5, negative 10. Okay? I really don't want to write that as a all fractions, but I guess they want me to. So let's do that. 9 over 2, negative 5 over 4, okay, 3 over 4. Okay, so that's our first way. Now let's do it the second way. The second way, what's the first thing you would do? Take the inverse of A. And what is the inverse of A? What's the first thing you would do with that? Find the determinant of A, and that would be 2. Okay? So the inverse of A would be
what you're doing is like the zip, like the number 2 that you wrote down, like AK minus 1.
Okay, say that again.
Are you doing like the little steps that you write down before we start the examples?
Okay. Oh, you mean what we think the answer is? We're actually calculating the answer to see what it is. What we're doing now is the inverse of A. See, this one we found A squared, that was here, and then we found this inverse, which is that.
Right, I understand, like, we're going, like, how we wrote down the problems, like, A minus 1 minus 1 equals A, well, A to the negative 1 power.
Yeah, we're doing A to the minus 1, and that means the inverse of A. Okay. That's first take the determinant, right? 4 minus 2 is 2, 1 over 2, times 4, 1, written like that, negative 1, negative 2, written like that, and then we can take that and multiply through, and what do we get? 2, negative 1/2, negative 1, 1/2. Now you can do that. Next thing you're going to do is square it, right? And frankly, I would rather square first and then multiply through. So even though we did that, I want to square first. And if I'm going to square this, that's 1/2 times 1/2, which is 1/4. And then what we're going to do is multiply this one by itself. I'm being real lazy here. Unlike Nigel, I don't really like fractions that much, but yeah. So I'm going to multiply this by 4 minus 1, negative 2, 1. We could have done the other thing. I think the book did. I just did it because you told me to. But what I want to do is this. Multiply those two by each other. The integral part of A, multiply it by each other, and then we'll multiply by 1/4. What does that give us? Say again? No, yeah. I've already done the 1/4. I'm going to multiply these two matrices by each other. That one by itself. One more time. Okay. 16 plus 2. 18. All right. 18. Next. Say again. Okay. Yeah, I would assume we're going to do 2, 1. So that'd be, 1, 2. 1, 2. How's that?
Okay.
So that would be
negative 4 minus negative 1. Okay. Plus negative 1, which is like 3.
Just what?
3.
Negative 4 minus 1. Don't go to subtracting on me. Negative 1, negative 4 minus 1 is negative 5. Which okay, that's good. Okay. Negative 5. Perfect. Okay, next. Okay, let's see. That would be -8, yep, -10, and 3. And guess what, folks? These two are identically the same. And why go to multiply through? If you can leave that factor of 1/4 out front, leave it out. It makes the rest of life a lot easier. That's only if you're lazy, though, Nigel. Okay, so, yeah. Okay. It does give you the same thing. And we could have multiplied that one, the second one with a halves in it by itself. You'd have gotten this one. It would have just been more work. But it would have come out the same. Guaranteed. What we did here, remember, we were taking this and squaring it. That's what this was. And squaring it is multiplying it by itself. So rather than multiplying this by itself, that would have been correct. It would have given you this. But I said, why not multiply this by itself? 1/2 by 1/2 is 1/4, and then this by itself is this, and that's exactly what we had here, so that is the same as that. So to me, it's just easier to do it before keeping the factor out there. The book threw the factor in and made you do all the work, but that was the book, not me. Okay. Note that either method produces the same result. Feels like, oh no. Yeah, just when we're just about to do a new theorem, we ran out of time. And that's exactly where we ran out of time the last time I taught the course. So we're almost finished 2.3. So homework exercises do any of the odds 1 through 5, any of the odds 7 through 29. Now, if 27 and 29 bog you down too much, you decide how long you want to work on those, okay? Do any of the odds 31 to 35. Either 37 or 39, or both if you choose. Now, notice when you get to 3x3s, don't try to use this method. You have to use the other method. This method doesn't have a corollary for anything but 2x2s. So then you have to actually augment or adjoin the identity matrix and do like that. Okay? Now, if you want to try to do some of the others past that, you can. I think we've done enough that you could, but that's about where we stopped. So go as far as you'd like, but go at least through 39. If you want to go a little further, you can do it. I'm convinced. Okay? Good deal. Any questions? All right. Well, I'll see all 3 of you, and hopefully the 4th too, again later this afternoon. Different classes, but same time. Those 2 in Cal 3, these 2 in differential equations. Okay, good deal. Have a good few hours working on your linear algebra and getting ready for your other courses. All right.